Okay, here I am practically in the same breath, going on into part two. Make sure that my video is actually rolling here. Yes, it is. We're in 8 seconds already. Okay, so this is part two. In case you're disoriented, where is my other, here we go. In case you're disoriented, we are right here, now looking at part two. And this is now on page 264. Okay? Chapter 13 still, in preparation for the coming test. All right, so number 25. How much force? Now this one, I think many students find this question kind of mysterious, like, how am I supposed to know? Well, number 25, 25. How much force is needed to push a nearly weightless but rigid 1-liter carton beneath a surface of water? Well, how do I know? Well, I'll tell you how you know. You know by remembering something I told you earlier. In fact, I mentioned it just in the previous review video, I think. Yes, I believe I mentioned it. And you also see it back in the sidebar of page 252, where they mention to you that a one liter of water has a mass of 1 kilogram. Therefore, a weight of 9.8 newtons, or we've been using 10 newtons. So 1 liter of water weighs 10 newtons. You've got an empty 1 liter can. You're pushing it under the water. There's going to be a buoyant force upward on it. Now, we're kind of ignoring right now the weight of the can itself, okay? So ignoring the weight of the metal can, or the cardboard, or whatever it is, you push that thing under. How much water will that 1 liter carton displace when it gets under the water? Yes, of course, it will displace 1 liter of water. If it displaces 1 liter of water, then what's the buoyant force on it? Remember, the buoyant force equals the weight of the displaced water. So if I push that thing under there, it's going to displace 1 liter of water. 1 liter of water has a weight of 10 newtons. So there's an upward buoyant force of 10 newtons. And if there's an upward buoyant force of 10 newtons, guess what I have to do to get it down there? I've got to push down with 10 newtons of force. Ta-da! We found the answer. It wasn't that hard. It can be done, provided you know that 1 liter of water has a weight of about 10 newtons. 9.8, but we won't tell. We can move on to number. All that time for just number 25. Number 26. Why is it inaccurate to say that Why is it inaccurate to say that heavy objects sink and that light objects float? Well, he says, give an exaggerated example. Okay. Here's a light object that sinks. How about a grain of sand? Very lightweight, but it definitely sinks. How about an aircraft carrier? Very huge weight, but it floats. What's the difference? Well, the sand weighs more than the water that it displaces. The aircraft carrier actually weighs less than the water it displaces. That's all there is to it. Buoyant force is all about displaced water weight, and whether something rises or sinks depends on how its own weight compares to the weight of the displaced water. Now, I don't have a script I'm going by here, so if at any point I find myself saying something that doesn't sound right, please let me know and I'll send out a retraction. But I think my words are all coming out very nicely here. Number 27 hurts my brain. I'm not sure I want to take time right now to really discuss number 27, but let's see if I can remember how this works. In my book here, I wrote myself a long note over here in the margin explaining it to myself. I might have to read that again. I did not read it in preparation for this today. A piece of iron placed on a block of wood makes it float lower in the water. Okay, yeah, because we're adding weight. You need to displace more water. It sinks down deeper, sure. If the iron were instead suspended beneath the wood, would it float as low, lower, or higher? Okay, without looking at my answers here, I'm going to think this through for a moment. If the iron, instead of being on top, is underneath, what will that do? Well, if the iron is underneath, the iron itself is now displacing some of the water, increasing the buoyant force. Okay, yes, my answer here says it will actually float higher. And the note I wrote says, either way, displaced water is the same. Of course, the displaced water is the same, yes, because the weight of any floating, this is the flotation principle, the weight of any floating object has to be equal to the weight of the water it displaces. But now, part of that weight is in the water, displacing more water, so it doesn't have to float as deeply anymore. Reading my note, either way, displaced water is the same, but now the mass is displaced. What? I can't read my own writing. Now the mass is displaced. So use disciples less or mass. Never mind, I can't read my own writing. Okay, number 28. Compared to an empty ship, would a ship loaded with a cargo of styrofoam sink deeper into water or rise in the water? Got an empty ship. It's floating. Someone pours in a whole bunch of styrofoam. Will that cause the ship to rise up or sink lower? Now, common sense in this case just might mess you up. As we've said many times before in class, back before the Corona days, in physics, common sense will often fail you. Common sense might say, oh, styrofoam floats really well, so it'll make the ship rise up. Well, wait a minute. If I pour in a bunch of styrofoam balls, does styrofoam have weight? Oh, yes. Okay, so am I increasing the weight of the boat overall? Yeah. So doesn't that mean that now it has to displace more water? Yeah, I guess so. So doesn't that mean it has to sink deeper in the water? Yes. It doesn't matter what the extra weight is made of, whether it's made of iron or styrofoam. If I'm adding extra weight, it's going to make the boat sink down deeper because more weight means more buoyant force is needed, which means more displaced water is needed. It will sink deeper. Okay, my notes now say that I need to jump all the way down to number 34. In answering the question of why bodies float higher in salt water than fresh water, your friend replies that the reason is that salt water is denser than fresh water. And then he adds in parenthetically, does your friend often answer questions by reciting only factual statements that relate to the answers but don't provide any concrete reasons? How would you answer this? Well, you're going to float higher in salt water. What was the question again? Yes. In salt water, the displaced water is going to weigh more. Yes, salt water is more dense than fresh water. Realize when you dissolve salt into water, that salt actually resides in little spaces between the water molecules and doesn't take up any extra volume. You can take a liter of water and put salt in it, and more salt, and more salt, and it'll still be a liter of water. Because as the salt dissolves, it goes in between the water molecules and doesn't take up any more space. Until, of course, you get it to the point where you can't fit any more salt in between the water molecules. That's called being saturated. And then if you put in more salt, it sinks to the bottom, and the level of the water starts to rise then. But in the ocean water, salt water is more dense than fresh water because there's more matter in the same unit of volume. So, if salt water is more dense, that means that salt water weighs more, which means it takes less displaced salt water to hold something up than fresh water. If it takes less salt water to equal your weight, then you're going to rise up higher because you don't have to displace as much water because the salt water is heavier. Make sense? Think about it. Moving on. Number 35. A ship sailing from the ocean into a freshwater harbor, sinks slightly deeper into the water. Does the buoyant force on it change? That's kind of a trick question. Does the buoyant force change? Well, wait just a moment. Hold on a second. If the boat is floating, the only way it can float is if the ship's weight downward equals the buoyant force upward, so the two cancel and it doesn't go up or down, it just floats. Remember the flotation principle. For a floating object, the displaced water weight has to equal the ship's weight. Okay, so if it's floating, has the ship's weight changed? No. And if the net force is 0, then the buoyant force must not have changed either. If the ship's weight doesn't change, suppose there was more buoyant force. Well, that ship would kind of like pop out of water. Or if the ship's weight hasn't changed and there was less buoyant force, then the ship would sink. But because the ship's weight is not changing and it's floating, then the buoyant force must not be changing. So it's the same buoyant force. How can that be? If it's gone into fresh water, why is it going to sink deeper then? Because it takes more displaced water, fresh water, to equal its weight. In the salt water, it takes less displaced water to equal the ship's weight. The buoyant force doesn't change. The ship's weight doesn't change. What changes is the density of the liquid it's floating in. We move on. Number 37. The weight of the human brain is about 15 newtons. Fascinating. 50, that's pretty heavy. Well, in case, this thing, which is rather heavy, this iron block here, it's not iron, sorry, brass block here, is about 10 newtons. But we're told here that our brain weighs about 15 newtons. Pretty heavy. Moving on, what's it say then? The buoyant force supplied by fluid around the brain is about 14.5 newtons. So your brain is kind of floating in liquid with a net downward force of only about a half a newton. Your brain is kind of barely settled on the bottom of your cavity in there, in this ocean of fluid. So your brain weighs 15 newtons. It's buoyed up with about 14.5 newtons. So there's a net downward force of only about a half newton. It's being gently suspended in the fluid. Feels kind of nice. But that's not the question. Does this mean then that the weight of the fluid surrounding the brain is at least 14.5 newtons? No. It has nothing to do with the weight of the surrounding fluid. It has everything to do with the weight of the displaced fluid. So the displaced fluid, where your brain is sitting, that space in there that would be fluid if your brain wasn't there, the displaced fluid would have a weight of 14.5 newtons. Not the fluid around the brain, but the fluid that the brain has pushed out of its way. The buoyant force equals the weight of the displaced fluid, not the surrounding fluid. Number 39. When an ice cube in a glass of water melts, does the water level in the glass rise, fall, or remain unchanged? Interesting. If we have, oh, there's my cat. No, that's not my cat now, that's my cat a long time ago. Hummingbird on my finger. Okay, stop giving me, I've got to put in my password. Yeah, Pat, sorry about, I have no idea how long I've been entertaining you with these pictures. Oh, okay, I thought I had to put in my password, I didn't. All right, that was too easy. So where was I? Forgot what we're doing. Oh yes, You've got a container of water. You've got ice cubes in here. Ice cubes, ice cubes. Everybody knows that ice cubes float, right? As the ice cube melts, what happens to the level of the water here? Well, ice is less dense than water, a concept that we'll be covering in more detail in a later chapter, assuming we get there. Ice is less dense than water. As the ice melts, it goes back to being the same density as the surrounding water. Another way of thinking of this, the ice cube is displacing its own weight in water, right? It's displacing, if it's displacing this much water, the ice cube is displacing its own weight in water. When the ice cube melts, has that frozen water's weight changed? No. So as it melts, the weight of the now melted water is still the same as it was when it was frozen. It's the same weight. It's now a smaller package because it has contracted some when it melts, but it's the same weight as it was before. Therefore, it's still displacing the same amount of water it was before. If it's displacing the same amount of water as it was before, why would this water level change? It will not. Try it sometime. Of course, if you pack in so much ice that the ice is hitting the bottom of the container and you pile it up on top like this, that's another story. Now as it melts, the level's going to rise because you packed in too much ice there. But if it's just plain floating, when it melts, the water level will not rise. He then asks another question here. Does your answer change if the ice cube has many air bubbles? And again, this is one of those things, kind of like number 27 that hurts my brain. Number 39 also hurts my brain. So I'm simply going to tell you the answer. If you have air bubbles in the ice, does anything change? Nope, no change. But how about if the ice cube contains many grains of heavy sand? Well, the difference is, if your ice cube has grains of sand, when it melts, that sand is going to go into the water and take up more space. And therefore the level would then rise a little bit. Oh no, the answer here says the level will fall. I would have to think about that way more than I have time to think about it right now. I actually have an answer key here. I could read the answer in Paul Hewitt's own words. Oh, maybe I should. See if I can find it real quickly here. Entertain yourself for a minute. Play a little solitaire or something while I find my... no, I can't find it. I had it here just the other day. There it is. Answers? Okay. This is chapter 13, right? Yes, chapter 13. And we're looking at, here we go, solutions to the exercises. Chapter 13 there. And this is number 39. Here's what he says. When the ice cube melts, the water level at the side of the glass is unchanged, neglecting temperature effects. To see this, suppose the ice cube to be a 5-gram cube. Then while floating, it will displace 5 grams of water. But when melted, it becomes the same 5 grams of water. Hence, the water level is unchanged. The same occurs when the ice cube with the air bubbles melts. Whether the ice cube is hollow or solid, it will displace as much water floating as it will melted. If the ice cube contains grains of heavy sand, however, upon melting, the water level at the edge of the glass will drop. This is similar to the case of the scrap iron in exercise 30. He doesn't explain the reason. Paul, come on. Didn't explain the reason. Okay, and I'm not going to think about it anymore. Number 40. So that was a waste of time. A half-filled bucket of water is on a spring scale. Will the reading of the scale increase or remain the same if a fish is placed in the bucket? That hits me as being a little bit obvious. Bucket's half full of water. Bucket is half full of water. We put a fish into it. Okay? You put a fish in, what happens? Of course, the water level is going to rise a little bit. We've added the weight of the fish, so clearly the weight of the bucket has increased. We just added weight to it. We added a fish. That part's pretty easy, right? Right. Now, will the reading of the scale increase or anything if a fish is placed? Okay. Will your answer be different if the bucket is initially filled to the brim? If the bucket is initially filled all the way to the top, and I throw, kerplunk, I throw a fish into the bucket now. Well, if I do that, some water's going to spill out. But guess what? The reason the fish is able to stay in one place, because the fish's density is the same as the water's density. So he's displacing his own weight in liquid. So we put weight in, and water weight is pushed out. So if it was filled to the top, you throw the fish in, does the weight of the bucket change? No. Fish goes in, water comes out, everything stays equal. Number 42. Would a fish float to the surface, sink, or stay at the same depth if the gravitational field of the Earth increased? Ooh, if we had more gravity. Oh. Well, if we had more gravity, if we suddenly put this guy into on a planet where there's more gravity than there is on Earth, what will happen to him? Will he float higher, lower, or just the same? Well, think about what happens. Does his weight increase? Yes. Does the weight of the displaced water increase? Yes. Therefore, does the buoyant force increase? Yes. So does it change his flotation in any way? No. Why not? Because yes, the fish's weight increases, but so does the buoyant force because the displaced water weight also increased. Nothing changes. So the fish wouldn't care the least bit if we put him into a place where gravity is stronger. Now, we would care. Go to a place where the gravity is twice as strong, and you're going to be kind of going, oh man, it's so hard walking. But in water, it wouldn't make any difference. Number 43. What would you experience when swimming in water in an orbiting space habitat where simulated gravity is 1/2 g? So it's rotating. You're walking around on the outer surface of this rotating space habitat, but they're not rotating it fast enough to give you a full 1 g, a full 9.8 meters per second of acceleration. You're rotating slower, so you only have a 1/2 g. You feel half your normal weight. It's like, oh, I used to weigh 160, now I only weigh 80. It's so nice. That's a good way to lose weight. Okay, so what was the question? I don't know what the question is. What would you experience when swimming in water in that environment? It wouldn't make any difference because you weigh less, but your displaced water would also weigh less. It all comes out even. Would you float in the water as you do on Earth? Yes. It's the reverse thing with the fish. In the greater gravity, he doesn't care. If we had less gravity, we don't care because our weight is less, but so is the weight of the displaced water, and therefore so is the buoyant force less. Everything is still equal, and we float just fine. Number 44, we say that the shape of a liquid is that of its container. But with no container and no gravity, what is the natural shape of a blob of water? Yes, we discussed this last time. Because of cohesion, the natural shape of a blob of water as each molecule is attracted to each other molecule, and the surface molecules are all attracted toward the center, the natural shape is spherical. Go online sometime, go on YouTube and look up something like, I don't know, maybe look up water on the space shuttle. I know I have some videos of blobs of water on, not the space station, but on the space shuttle, blobs of water forming this nice, beautiful sphere. You can have a sphere of water hanging here in front of you in the space station and take a straw and stick it in there and watch that blob of water just shrink. It's pretty cool. Its natural shape is a sphere. 47. We've got this situation that I illustrated for you before. We've got this strangely shaped container here. We've got a piston sitting here. We've got another piston sitting here. We know how this works, remember? If I put a certain amount of force here, say 10 pounds of force, if this surface happens to be 50 times larger, then I would, and this, then this, if this is like 1 inch, square inch, and this is 50 square inches, with 10 pounds per square inch here, I'm going to get 10 pounds per square inch there. So if this were 50 square inches, I would have 500 pounds of upward force by pushing with just 10 pounds downward. Pretty cool concept. But the reverse is also true. Huh? Yeah, the reverse is also true. In order to lift this 10 pounds here, I have to press down here with 500 pounds. Yeah, say that again. The reverse is also true. To lift this 10 pounds here, I would have to push down on this side with 500 pounds. I don't think the dude in number 47 is going to be able to do this. It's not happening. He isn't heavy enough. Forget about being strong enough. If he stood on the thing, he wouldn't be able to do it. Okay, moving on to number 50. I know that I'm changing the numbers here. I'm a little surprised to see that they're using, I just happened to randomly chose 50 times, and that's exactly what they're using here. We're raising 10 kilograms though, a 10 kilogram mass. Anyway, I changed the numbers a little bit, that's right. Number 50. On the surface of a pond, it is common to see water striders, insects that can walk on the surface of water without sinking. What physics concept explains this fact, this act? That would simply be surface tension. Remember that surface tension makes the surface of the water act like, even look like, it has like a skin on it, but there is no skin. That water on the surface is just as wet as the water down below. It's not like it's got this solid film on top. No, it acts like it has a skin on top, but it does not. Surface tension. For a review of that, go back and watch the videos of part 4, part 3, whatever the last one was. Rewatch that to see a review of how that works. And that is the end of the review assignment. And we stop there. Test will be coming soon. You'll get emails regarding the procedures for the test. The test will be emailed to parents, and then the parent will proctor the test and sign the test, and then scan it or take a picture of it and send it back to me. Of course, books are to be out of sight. Phones are not to be within your reach. Laptop computers not within your reach. Usual home test taking procedures, proctored by a parent. So that'll be sent to the parents to be printed out and handed to you when you're ready for it at some point in the near future. Watch your emails. And that's it. Enjoy the test, and see you later.